Good afternoon, Year 10, soon to be Year 11, wonderful triple chemists. So, third time of me still not having properly met you apart from doing a bit of cover at the end of last term. And we are on to combustion, and more specifically the equations we use to describe it. Now, I'd like to apologise in advance for me trying to write with a mouse. I do not have access to a pen board to be able to do this on my PC. So this will be mouse writing, I'm afraid. Sorry in advance. Yeah, just sorry. There's nothing really I can say apart from that. So we're looking today at combustion. Before we do that, I've got some questions for you to have a very quick go at that should be incredibly easy. So these are starter recap questions. And here we go. So please have a read and do your best to answer them. Notice they're not all true or false, and they're not always pick the correct one. Sometimes they're please talk about all of the things here, and that's slightly confusing. But have a go, pause, and then I'll go through the answers in a second. Okay, so hopefully you've paused and have written your answers because I'm about to go through them. So hydrocarbon contains and oxygen? No, because it's a hydrocarbon, so that is atoms of hydrogen and carbon only is the correct answer for 2 marks. Crude oil is a mixture of different sized hydrocarbons or a single liquid compound. We should hopefully be very well aware it's a mixture, otherwise fractional distillation would be a waste of time. 3. We can separate mixtures using distillation or fractional distillation. This uses not the mass. Mass has very little effect on boiling point actually. It is the boiling points that are key. Mass is a very small contributing factor to boiling point, but it's mostly to do with intermolecular forces, the bonds that hold the molecules together. Okay, number 4. How does the length of the hydrocarbon chain affect the boiling point? Well, increasing length increases the boiling point. The longer the molecules, the greater the intermolecular forces, the more energy required to boil them. B. The thickness or viscosity. Once again, increasing chain length increases viscosity, making them less runny. Apparently there's a bit of my mouse map there that doesn't do straight lines. There we go. Thickness or viscosity of hydrocarbon increases with increasing chain length, again due to those intermolecular forces, increasing in strength or number. It's going to be fun writing the equations later. Okay, 5. A hydrocarbon catches fire easily. What word would we use to describe that? That's flammable. I'm not going to write that here. 6. Apparently I am. Please don't crucify me for spelling of things. It's just getting it to look even vaguely like English is going to be a major achievement today. Hydrocarbons that catch fire easily are the long chains or the short ones. They are the short ones. Short ones are the most flammable. Though I've written small, but that'll do. The short chains, of course, more volatile, weaker intermolecular forces, so much more readily able to burn. Lastly, is it true or false that hydrocarbons that are smaller in length come off highest in the fractional distillation column? That is true. Smaller ones do come off higher at the lower temperatures. So remember, it's hot at the bottom and cool at the top. As you go up, it cools down, so the shorter chains with their lower boiling points will condense higher up the column. Okay, so what we're really looking at in today's lesson is combustion of hydrocarbon fuels. Now I'm being specific here, we're only going to talk about hydrocarbon fuels. Well, that was nice. Okay, apparently I have an email and I haven't muted it, so sorry about the ding dong, and I hope that wasn't too loud and offensive for you. So, when we burn stuff, we get energy. This is incredibly useful, and it's called combustion. But most importantly, it's an oxidation reaction because it's reacting with oxygen. Now, oxidation reaction of hydrocarbon fuels, the burning, can produce a variety of products depending on the amount of oxygen present and how completely things burn. I mean, if you reduce the temperature, you can persuade things to burn incompletely at really low temperatures, even if there's enough oxygen. But realistically, hydrocarbons burn so well that actually, in general, it's the supply of oxygen that controls whether or not you get incomplete combustion. I suppose that's not true of the big molecules. Really big molecules can burn incompletely, even at room temperature. That's why diesel engines give out more unpleasant particulates than, say, a petrol engine, because the particulates are basically the longer chain diesel not having time in the engine cylinder to burn fully. But like I said, there's also a lack of oxygen component there as well. So, the amount of oxygen controls what products we get. And now there are 2 types of combustion. We have complete combustion and we have incomplete combustion. So these two types of combustion are fundamentally about whether we've got enough oxygen. So you're probably aware of complete combustion. The best example of this is a Bunsen burner flame. When you set it to blue, or the heating flame, that is it undergoing complete combustion. You notice the flame is very, very hot, no smoke, and the flame gives a nice roaring sound as it draws air and blasts it out of the top of the Bunsen burner due to the convection from the heating and just mixing with the gas. So complete combustion occurs where there is excess oxygen or sufficient oxygen, and this means that all the products are fully oxidized. Yeah, that's right. So whatever the reactant molecules were, all of the elements present have been fully oxidized, so all the product molecules are as oxidized as they can be. So carbon dioxide and water are both the most oxidized it's possible for carbon to be, and the most oxidized it's possible for hydrogen to be in this context. So we've added oxygen, and we've added oxygen in both cases to the maximum, effectively. Now, incomplete combustion, however, occurs when we do not have sufficient oxygen. We only get partially oxidized products. Now, normally hydrogen is much keener at the whole oxidizing thing than carbon is, so we tend to always get water regardless. However, we do also get other things, and complete combustion is not as neat as incomplete combustion is not as neat as complete combustion, because I can't say in an equation I will always get only, say, carbon monoxide or carbon and unburnt hydrocarbon particulates. Excellent. I really need to close that email. Nope. Sorry, not going to do that now. CO and C. I can't say I will get entirely that, none of that, or entirely that, none of that, or all of this and not anything else. Incomplete combustion just creates a massive mixture of all of the different possible options, and depending on how much oxygen, you'll get more of some and less of others, and on a second-by-second basis, depending on where oxygen is most available, you'll get complete combustion happening in certain patches of the reaction, very incomplete combustion happening somewhere else, and you'll just get this big mixture forming. So it's not really easy to say this always produces this, 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 and this. It's just these are things that might form, and the relative quantities is unknown, at least until we measure it. So don't expect this to be a specific one, and if the exam wants you to write equations, they will tell you what you have to write in those equations. They can't just say write an equation for incomplete combustion. Well, they could, but they can't mark you wrong for just doing an example. You don't have to try and fit everything in there. Okay, so balancing combustion equations. First of all, I don't know you guys. I have heard you are brilliant. So I'm going to assume that you can largely do this and not spend the rest of the lesson balancing equations. Historically, every time I teach this combustion lesson, I tend to find out that whatever year 11 class I'm currently teaching, even if it's my triples, I mean the year before last triples were pretty decent effort, but last year's triples needed a bit of extra help on the balancing combustion equations. So we spent quite a long time, in fact we just spent the lesson practicing balancing equations specifically on combustion equations. Same with my combined scientists. So let's have a look. I believe you lot should be quite good at this, but you know, everyone struggles with balancing equations initially, and some people take that struggling for a little while, but you will get it, and don't panic. So I'm going to do a brief run through of how we do it, particularly in the context of these hydrocarbon combustion reactions, and then hopefully you will have the skills already to answer the questions without my further assistance, although I will do my level best to give it later in the PowerPoint. So I use a method called the scoreboard. If I find an equation that I can't balance by what I call inspection, I look at it and work it out. Then I use a method called the scoreboard. And I don't usually have to resort to this these days because I've got a fair amount of practice at balancing equations. I've been doing this for a number of years now, and I was doing chemistry quite a long time before that. So this is a method I use in extremis. If I come to something that's really hard and I get lost somewhere about halfway through balancing, I'll use this to show me what I'm doing and make sure I don't get it wrong. It's what I strongly suggest you do if you are looking at an equation and you're not either completely confident or you just have a little bit of a doubt and you want to just check your answer at the end. So, step one, write out the equation as best you know. you may be doing this, they may not have given you the equation, they may be asking you to complete it from a word equation or something. 2. So below the arrow in the symbol equation, list all the elements present. Now, of course, you should have the same elements present on both sides. If you haven't, something's gone wrong. Either you've missed off a product or a reactant, or this is not an equation that could work. So we've got I will do some examples of these in a little bit, don't worry. 3. Write out next to your list of elements on the left and the right how many of each atom are present, remembering to multiply by little numbers and then by any big numbers in front of the species. And if you've got that element present in multiple species, making sure that you add those together as well. So you then have a situation where you've got a list of elements and a list of how many of them there are present on each side of the equation. The next step is choosing one element at a time, and there's a good order to do this in, and it's the one which has the occurs in the most places should be done first, and the ones that appear on their own somewhere should be done last. Add big number multipliers, which go in front of a species, and their proper name is stoichiometric coefficients, though you'll never be asked about that name at GCSE, until each element has the same number of atoms on both sides of the equation. As you do that, update the scoreboard, so you've always got a sort of a running total of how many elements there are. And then you can come back at the end and just check that A, the numbers are the same on both sides, and B, that your scoreboard does actually represent what you've written in the equation. If you do that, it's a trial and error thing. Sometimes you'll get to a point where they don't add up, but they need to add up, and that means you may just have done something wrong, in which case just try putting a different big number in front of one of the things, and that may solve it. Sometimes a 2, which is the obvious place to start, doesn't work, and a 3 or a 4 might make a difference. Generally, if 2 doesn't work, 3 is good. Okay, the last rule. You can't change the formulae at all. That includes the little numbers, the mole ratio of atoms in the compounds. You can't change those numbers, and you can't change the actual atoms present in the formula. So never ever change those little numbers. Okay, I've got some questions for you. Now, I'm going to ask you to pause and have a go at these. They're going to rely on work we've done previously. So you might want to access your notes from the last few lessons. So here they are, 5 questions, getting progressively more difficult, and using examples. You notice I've told you what I want in terms of the product. So you're going to have to write out the word equation first, and then the product I've asked for. So complete combustion, that's going to be carbon dioxide and water. Incomplete combustion, there's going to be water and whatever else I tell you. So pause now, have a go at those. I want the symbol equations and the word equations. Do the word equations first, and then do your best to write symbol equations. I have included alkenes and alkanes, just to trip you up. I say plurals, there's only one alkene, but just keep an eye out for it. Okay, pause and carry on. So, the answers. Let's have a look at how we do this. Oops, there's the question. That's useful. So here should be the answers. I'll animate up the questions. Now, I have done these, but there's always a scope for making mistakes, and it's entirely possible I've got this wrong somewhere, like a typo generally. However, what I'm going to say, oh look, another email, excellent. What I'm going to say is, if you don't have these answers, the next few slides I'm going to work them out, and if by any chance you find that your answers, having followed my method, still don't make any sense, then that's a good time to drop me an email. However, if you have got these answers, then the next 5 slides are of limited use to you, and you probably want to skip forwards. As I haven't recorded it yet, I can't tell you how far in the MP4 to skip forwards, because I won't know until I've encoded it in MP4, whereupon I won't be able to say it now. So I'm stuck in a bit of a catch-22. However, pretend I have used that knowledge and I've told you where to skip onto, and it's after we stop trying to draw equations with a mouse. Okay, so let's have a look at actually working out these answers. Okay, so apologies for being slightly patronising. This is how I do a scoreboard method. First off, what's our question? Well, methane plus oxygen. Hopefully you all know that methane is CH4, after me going on about it for a couple of lessons, and oxygen is O2. I haven't said anything about that at all, but you really ought to know that by now. Complete combustion, I said, formed water and carbon dioxide, so CO2, let's try that, and H2O. This is harder than it looks. My writing is terrible, I'll accept that, but writing with a mouse is a challenge. Right, the scoreboard method. I like to see a list of all the elements present. Now I wouldn't find it necessary for this question, and many of you won't have done either. But if you were, this is how we would do it. Carbon, hydrogen, and oxygen are all the elements present. Now initially, I've got 1 carbon on the left-hand side, 4 hydrogens on the left-hand side, and 2 oxygens on the left-hand side. On the right-hand side, I've got 1 carbon, 2 hydrogens, and 1, 2, 3 oxygens. So my problem is both my hydrogen and my oxygen. Well, hydrogen occurs in 2 places, but neither of them are elements, whereas the oxygen occurs in 2 places, but one of them is an element. So we're going to fix hydrogen first. Oh, sorry, oxygen's in 3 places, so yeah. That seems to contravene my rule of do that first. Don't do it first, do it last, because it's an element here. Okay, so hydrogen, 4 on this side, 2 on this side. What do I multiply 2 by to get a 4? A 2. Okay, now that changes my scoreboard down here because that affects both hydrogen and oxygen. So that 2 times 2 hydrogen means I've now got 4 hydrogen. That 2 times 1 oxygen means I've got 2 oxygen there, and a further 2 oxygen there. I've now got 4 oxygen. Okay, so far so good. Carbon is already solved, I've not touched it. Hydrogen is now solved, just needs oxygen. And there's an element on this side, so I can simply multiply that 2 by 2 to make 4 oxygen. That's now balanced, it's done, I can check it, and it's sorted. Next one. Oh look, I keep forgetting to animate that. Let's animate that now. Propane plus oxygen. Okay, so we're starting off with propane, which is C3H8, 2N plus 2, remember? Plus oxygen again. Now this time, the product I've said is carbon plus water. Remember, water is assumed, and we're forming carbon. They may well tell you that this forms water if they want you to write down a similar equation about combustion, or incomplete combustion, but if they don't, assume it. So C3H8O2 makes carbon and water. Okay, so let's get started. We need our scoreboard. We need carbon, hydrogen, and predictably enough, oxygen. Starting off with 3 carbons, 8 hydrogens, and 2 oxygens. 1 carbon, 2 hydrogens, and 1 oxygen on the right-hand side. Okay, we'll start with carbon, because it doesn't do very much here. I know it's elemental on this side, and so you could argue that I shouldn't do it now, but it's not going to make any difference. So I need to multiply that by, let's have a green pen, multiply that by 3, which turns 3 carbons. Almost too easy to do that one now, you shouldn't do that one first. However, let's look at hydrogen. This is the one we should have started with. Hydrogen, 8 here, and 2 here. What do I multiply 2 by to get 8? 4. That changes my number from 2 to 8 by timesing by 4. Okay. That, of course, affects my oxygen. I've now gone from having 1 oxygen to having 4 oxygens. Okay, fair enough. That means I'm going to do something about this oxygen on this side. I've got 2 currently, I need 2 more. Multiply by 2 to get 4. Okay, 3 carbons, 8 hydrogens, 4 oxygens. Done. Ethene. This is the one with a slight trick. C2H4. Oh look, it's an alkene. So hopefully you've got the 2N, not the 2N plus 2 formula there. Once again, we're burning in oxygen because this is all about combustion. Now this forms a complete combustion CO2, O looks slightly more like an O, plus H2O. Let's have a scoreboard. C, H, and O. Truly exciting. Okay, left-hand side, carbon 2. This does get boring pretty quickly. If you've managed to get this far without getting bored, well done. C2H4 and 2 oxygens. On the far right-hand side, on the right-hand side we've got 1 carbon, 2 hydrogens, and 1, 2, 3 oxygens. Looks very similar to the first one so far, doesn't it? Well, this time I can start with carbon because it occurs on both sides in one place and doesn't have any elements present. So let's have a go at that one. I'm going to do my 2 on this side, 1 on that side, so I need to multiply that by 2, which will get me 2 carbons there. It will also affect oxygen, making that into a 4, plus another one there, making it 5. Now, hydrogen. Slightly trickier. I've got 4 here And currently I've got 2 there. Well, that's alright. I can just stick a big 2 in front of that, and that'll make that into a 4. Conveniently, that also affects my oxygen. So what was 5 oxygen is now 1, 2, 3, 4, 5, 6. Which is good because it's now an even number. If that comes out as an odd number, you're going to have to multiply everything, because I can't put decimals or fractions here. This time, when I say here, I mean here. This time I'm going to be putting a 3 in front of my 2 oxygens, which will multiply up to make 6. If I check, 2, 2, 4, 4, 6, 6, which is a 3, 2, 2. Brilliant. Number 4, where it gets tricky. Oh look, I didn't animate the thing. Question 4. Propane, C3H8, 2N plus 2. It's an A. Plus oxygen makes carbon monoxide, which makes this a little bit more difficult to balance. CO plus H2O. Because odd numbers of oxygen make things hard, as you will find out hopefully. Or as you have already found out hopefully. And hopefully sorted it. So on the left I've got carbons times 3, hydrogens times 8, and oxygens times 2. On the right hand side I've got 1 carbon, 2 oxygens, and 2 hydrogens. So, as per usual with balancing these combustion and hydrocarbon equations, I like to start with carbon. You could start with hydrogen, it doesn't really matter. We're going to start off by going, oh, I've got 3 carbons here, I've got 1 carbon here, let's fix that. That gives me 3 carbons here, but it also changes oxygen. So now I've got 3 oxygens plus another one is 4. Okay, now I'm going to solve my hydrogens. I've got 8 hydrogens here and 2 here. Let's stick a 4 there. So my 2 becomes 8, but I've changed my oxygens again. So my 4 and 3 oxygens means I now have 7. This is where it gets slightly difficult. Okay, I want 7 over here. Currently I've got 2. What do I multiply 2 by to get 7? What are those of you who say 3.5 or 3.5? But you're probably aware that I'm not really supposed to have decimals in this until A level. Well, you're not aware of that. You've probably been told not to use decimals or fractions in your equations. You probably haven't been told not to do it at GCSE. For some bizarre reason, they don't think you guys know decimals or fractions, and so they don't like having them in equations at GCSE. They're fine with it at A level because, you know, the decimal value of a mole is still just a sensible number of things. It's just half of a mole. But, yeah, I don't know why. Apologies on behalf of the education system for you not being allowed to put decimals here. But we can solve that problem relatively easily. I'm going to actually ignore the scoreboard now. The scoreboard is now correct. That should be 7. Sorted. 8 and 3. But what I'm going to do to get rid of that unsightly 3.5 that the exam board dislikes so much is just multiply everything by 2. Now if you want to be a stickler and keep the scoreboard running, feel free to do so. If I stick a 2 there, I'm just going to double everything and make all the stoichiometric coefficients twice as big. So that one was an invisible 1 and is now a 2. That one was a 3.5, so it's now a 7. That one was a 3, so it's now a 6. That one was a 4, so it's now an 8. And my answer is 2, 7, 6, 8. Oh look, there's the start of it. Okay, question 5. And let's have that animate up again. So, there may be some background noise now because I think my smallest child is coming from the garden, which he will not want to do. So apologies in advance for that sound. So, my equation now is butane plus oxygen. C4, it's an A, so the H is going to be 10, plus oxygen, O2, makes CO. Oh no, it's CO. Not CO2, I'm doing incomplete combustion. Ooh, that's a highlighter. CO plus H2O. Now, this is very similar to the last one. So if you want to have, if you didn't get number 4 right, or number 5 right, and you've just watched me do number 4, please try and do this without my assistance, and then I'll do it. Okay, assuming you've now unpaused, if you were ever paused, I've got carbon, hydrogen, and oxygen. And I've got 4 carbons on the left-hand side, 10 hydrogens on the left-hand side, and 2 oxygens on the left-hand side. Whereas I only have 1, 2, and 2 respectively. That starting number is pretty similar if you've got carbon monoxide each time. Okay, I'm going to cheaply do carbon first, because I like doing the carbon first, it's just how I've always done it. I've got 4 there, I need 4 there, let's have 4 there. That of course changes oxygen, we've now got 4 plus 1, so 5 oxygens. Okay, I've got 10 hydrogens here, so I need to stick a 5 there. Oops, that's the worst 5 I've ever written. Which of course means that's 10, but now I've changed my oxygen. 5 there and 4 there. Means I've now got 9 oxygens. That almost looks like a 9. Almost. But not, you just do that again, shall we? 10, 9. I think that's marginally better. Okay, so what do I multiply 2 by to get 9? Well, 4.5. But once again, your exam board's irritatingness means that we're not allowed a 4.5, so we're going to have to put 2 there, doubling that, which was 1, now it's 2. Make that 9. I have 4 there, which is now 8, and I've got 5 there, which is now 10. If you completed the scoreboard, of course, you've now got 8 of those, 20 of those, 18 of those, 18 of those, 20 of those, and 8 of those, which is a nice large number of everything. That's still not a very good 0, but never mind. Okay, moving on. I'm now going to ask you to do some things yourselves a bit. This next bit, there's quite a lot of research you can do here, and I'm going to get you to do that yourselves and see what you can come up with. We'll discuss it again, and I'll see if I can come up with a key set of simple notes to get you the key ideas across, but it's quite fun to do this as research because you can find all kinds of cool stuff yourselves. So, problems with crude oil. You're probably aware that crude oil is, well, let's simplify, bad. Yes, it's done some amazing things for us, like industrialised our world, but it's probably going to have a significant impact on our future. And we're talking apocalypse level, significant impact on our future. So it has some downsides. Let's look at an example. When we get crude oil and we fractionally distillate from it, we get loads of useful things. But the fractions are not pure, they are still mixtures of hydrocarbons, and even then, those fractions are not pure hydrocarbons. The formation of oil entraps other elements. It's made of creatures. Creatures are not just carbon and hydrogen. So other things get involved as well, and one of the problem ones is sulfur. So, when you remove oil from the ground, it's not all the same particles. It has impurities present in it. Oh, look, I've got to animate each of the crosses out separately. And that sulfur present, actually this is more true in coal than it is in oil, but some of the longer chain oil molecules can contain some sulfur, so things like diesel, heavy fuel oil, some sulfur present in those, but it's mostly coal really. Now this sulfur, of course, when burnt, makes sulfur dioxide. So one problem example is an impurity present in the material itself, in the hydrocarbons themselves, which can be burnt to form a problem substance. But we've got a few other problem substances we produce from combustion. Let's have a quick look. So, these are the problem substances. This is, of course, by far and away the biggest problem substance. Even with perfect, complete combustion, carbon dioxide is still produced. Interestingly, I forgot to mention for incomplete and complete combustion one of the disadvantages of incomplete combustion, in fact any of them. So complete combustion, we've said, produces carbon dioxide and water, whereas incomplete combustion produces a whole variety of different things. Now, one of the key problems of incomplete combustion is that it doesn't release as much energy. You're not burning as much of the fuel, so you're not going to release as percentage of the stored energy as possible. One of the other problems is many of those products are unpleasant, and we'll have a look at exactly how unpleasant those products are in a second. So other than it being less efficient for using the fuels, it also produces a load of things that are at least as unpleasant as the products of complete combustion. So, carbon dioxide is one of the first things produced, and we know that has a significant impact on the world as it contributes to greenhouse gases. Sorry about the background noise. Apparently we're going to animate number 4 next. This produces carbon monoxide. This is the less oxidized form of carbon, and it is amazingly, amazingly toxic. There are occasional horrible news stories where people go on holiday to Spain. I really apologise for the background. Sorry about that. My small family are having a little bit of a meltdown, apparently. So, carbon monoxide, as I was saying, this is an extremely toxic gas. It forms fairly permanent bonds to your hemoglobin. Another email, excellent. And another, you do see in the news, not very frequently, thankfully, but sometimes, some tragedies. I'm remembering one from maybe 5 to 10 years ago, where a family went on holiday in, I think it was Greece, and the apartment they rented hadn't had a decent gas safety check for a long time, and the boiler was malfunctioning, burning incompletely and producing carbon monoxide. And the family went to sleep, and only one or two of the adults woke up, because adults tend to take longer to saturate with carbon monoxide than children. And if you have carbon monoxide, it's an odourless gas, it makes you sleepy, and you don't know it's a hazard, you just kind of get a bit drowsy when you fall asleep, because it's preventing oxygen from being transported to your brain. Your brain takes that as being, oh, it's sleep time. And then if you remain in the atmosphere saturated with carbon monoxide, you just get less and less oxygen to your brain until your brain stops functioning and dies. So carbon monoxide is really nasty. And I would strongly recommend making sure you have carbon monoxide alarms in your house, because you can't see it, you can't smell it, it just makes you sleepy, and so does light makes you sleepy, so it's quite hard to detect a indicative test for its presence. And yeah, be aware of it. If you get drowsy and it's not the right time of day, check your boiler, open the windows, that kind of thing. Your boiler, if it has soot marks or soot streaks on it, or is burning a yellow flame in the pilot light, if it's an old-fashioned boiler that has a pilot light, then there is a significant chance it's producing carbon monoxide, and it's extremely dangerous, so, be aware. Our third one, carbon particulates. If you don't burn things properly, you end up with, this is effectively soot, or fragments of hydrocarbon that have been not combusted. Now these can make thick, smog-like smoke. They can coat things, leaving that black smearing I was talking about that you could look for on a boiler to check if it's burning properly. You've probably seen a Bunsen burner flame when it's on yellow. If you hold glassware over the top of that, it's coated black quickly as fragments of soot and unburnt methane stick to the bottom. So that's mostly carbon, and this is unpleasant stuff, very bad for respiration. It's all in the news recently, nanoscale particles you can inhale. Some of these nanoparticles are caused by incomplete combustion and the soot particles that are formed. We have got water vapour. Now, actually, this one is really not a particular problem from combustion, because whilst it is the most important greenhouse gas in terms of quantity in the atmosphere, it contributes a far larger percentage of global warming greenhouse effect than anything else. It's also got very short half-life in the atmosphere. It tends to naturally remove itself in hours or days by, rain, etc. So that's not such of a problem. And then we've got sulfur dioxide, very unpleasant gas. It's not good for your lungs. It is not good for you at all. Triggers and causes asthma. It is pretty toxic. It is generally horrible. It also, if you dissolve it into water, say a cloud, forms sulfonic acid or sulfuric acid, and this makes rain acidic, so that creates acid rain. And the oxides of nitrogen, again, also extremely bad for your lungs. Again, feel free to look at recent news stories about diesel cars and emissions. These oxides of nitrogen can cause significant damage to your respiration system, but some other nasty side effects, triggering and causing asthma type things. And they're produced not from actually the fuel itself, but when fuel is burnt, it can get hot enough to actually cause the nitrogen in the air to react. Now this is fairly specific to petrol cars, although no, you're right, it happens to diesel cars as well. In a petrol car, it's the spark of the ignition, the actual spark that fires the spark plug, that causes the nitrogen to burn with oxygen. But diesel cars can attain temperatures high enough to burn burn nitrogen as well. So they smash nitrogen molecules apart and then form oxides of nitrogen, which can be sort of countered with a catalytic converter, but I'll let you research that in your homework, as homework of the work. So sulfur dioxide, oxides of nitrogen, these are the key list of problems. Particulates, carbon dioxide, carbon monoxide, sulfur dioxide, and oxides of nitrogen. So what issues do these cause? Well, the four big issues you need to be aware of. Global warming, which isn't a particularly accurate phrase. I mean, the world is warming, but we tend to talk about climate change now, because that net warming causes cooling in some places, warming in other places, not much change in temperature, but massive change in weather in other places, changing weather currents and ocean currents, and all kinds of unpleasantness that destabilizes and causes extinctions of life forms, etc. Acid rain, of course. What could be better than acid falling out of the sky on you? Well, this isn't going to ever burn your skin, at least not unless we somehow manage to significantly increase the concentration of acid in the atmosphere. but it is a serious problem for plants that are pH sensitive and water-based freshwater organisms that are pH sensitive. As a change in pH in a river can kill pretty much everything in the river, and a change of pH in the soil of a forest can kill all the trees in the forest. Global dimming. So particulate matter getting into high altitudes, so really fine particles getting to high altitude, can cause cloud formation, because condensation doesn't really happen unless there's something for particles to stick to, for water particles to stick to. You need nucleation for state change to occur normally, which means you can do supercooling and superfreezing, superheating of water. Just for the record, don't superheat water in a microwave. It's extremely dangerous. You can do it, just please don't. You need distilled water, a perfectly clean and with entirely scratch-free glass, and you need to remove the rotating platform. And then you can microwave water to well above 100 degrees C, and as soon as anyone touches it, stirs it, or puts anything into it, it will explode, because it'll all boil at once, and burn everybody horribly. So superheating water, bad idea, don't do it. Also, you're probably going to have difficulty getting hold of distilled water unless you are someone who runs a steam iron and doesn't like limescale, or keeper of tropical or marine fish. Lastly, photochemical smog. So, as we mentioned when we were talking about the reactivity of alkanes, I said they were basically inert, but that's not quite true. UV light can break up the chemical bonds, particularly if there are things like halogens present, and this can cause free radical action. And so photochemical smog is basically smog, which is kind of like a fog made of smoke, but which in sunlight breaks down and forms active chemicals, radicals. So photochemical smog is a hydrocarbon fog that is in sunlight broken down to form free radicals, which are extremely dangerous little particles that are very, very keen to react with anything. And I believe radical oxygen is one of the key things that cause aging in humans. So that's oxygen. You know, I know oxygen is toxic in large quantities, but in small quantities it's required for life. If it's inhalation of oxygen that ages you, imagine what inhalation of radical, hydrocarbons might do to your lungs, etc., and your cells. So photochemical smog is also bad. There's some nice pictures of China when it wasn't in lockdown, where you can see, well, not just China, in lots of places you can see this effect really clearly. But over big semi or fully industrialized cities, when there's massive traffic, you can just see a sort of yellow haze, and that is this huge cloud of smog hanging over the city, being rather unpleasant. So, we've discussed the key substances and mentioned briefly the key problems. What I'd like you to do is tabulate them. So your main task, other than the balancing of the equations for this week, is you'll need bigger boxes than this, but caused by, effects are, and mitigation. So what causes global warming? What effect might or is it having? And what are we doing to minimise those effects? Now this mitigation box is things we currently have, so technology we currently have that we are using to try and minimise the impacts, or technology that is just about to be rolled out that we could use to minimise the impact. So for global warming you could say things like moving to use renewables, burning fewer fuels, burning fewer fossil fuels, that kind of thing. That's a mitigation. You could talk about carbon capture and storage, as long as you say this is not a thing that works yet. Okay, global dimming. This is a really fascinating one. It's worth having a read of how we discovered this, because we always think of 9/11 as having absolutely no upsides whatsoever, and it's nice to find that even in that absolutely horrendous scenario, that a tiny bit of scientific light came out of it, and the grounding of all planes across America for 3 days caused the surface temperature to rise significantly, and everyone went, whoa, what's happening here? And it turns out that aircraft at high altitude put lots of tiny particles into the upper atmosphere, which create very, very fine cloud layers, who work brilliantly as mirrors and block some of the sun's energy. And of course that's then been suggested as a way of combating global warming, because, if you can't fix something in the difficult way, why don't you try fixing it even worse by pumping loads of particulates into the atmosphere? Because that'll go well. So anyway, that could be a mitigation up here. How can we deal with this? Well, we're working on that. I'm sure you can find some mitigations for global dimming. Effects, that one's fairly obvious actually. It's just an overall reduction in temperature compared to what it would be without it. Acid rain, what causes it? That's the oxides of nitrogen, oxides of sulfur particularly, forming the acids in clouds. To a lesser extent, rain is normally acidic because of carbonic acid from carbon dioxide, but that's kind of unavoidable. effects and what can we do about it, or what have we done about it, and photochemical smog, what it's caused by, what the effects are, and anything we can do to avoid it. I would like you to make sure that you include with this one and this one what a catalytic converter is and how it works, preferably with 1 or 2 simple equations. There are lots, so the simplest one is probably the one you're looking for, which is basically just converting nitrogen oxide and carbon monoxide, nitrogen monoxide and carbon monoxide back into CO2 and nitrogen. That's the one you need to know about. So please spend some time, do some research, draw me a beautiful table, fill it in with lots of lovely information, and then take a photograph of it and send it in to me for your homework. Thank you ever so much. I'm sorry about the screaming. I'm sure they're fine now they're eating. Have a lovely day, and take care, stay safe. Bye.